It's about the spatio-temporal process. So thank you very much.
Good morning to everybody. First of all, I would like to thank the LML, Isaac, Chloe, that organized this amazing summer school, and also all the people who shared with me this wonderful month here in ICTP, because I really enjoyed my time here. Today I'm going to present my project, the spatio-temporal Hawkes process, and its estimation via the so-called stochastic reconstruction algorithm, supervised by Zhuang Xiankang. I will give a brief introduction about what a point process is, what a Hawkes process is, and why is it useful, and I will get to its application, to its original application to data about crimes happening in Castellón and car accidents happening in Rome. First of all, what is a point process? A point process is just a random object whose realizations are point patterns over some space. The good thing about point processes is that whenever we can assume bounded finiteness, that means that in any small set of the space on which it evolves, there is only a finite number of points, we can define it in a well-defined way, simply specifying the conditional intensity rate. The conditional intensity rate is the probability of one event happening in a very small portion of the space. If we define this conditional intensity rate, we can define the point process. These point processes are very useful to model the happening, the occurrence of events along whatever kind of time or space domain we prefer. And so they're very useful for different applications, and literature is rich of a variety of models that can model events that respect some hypothesis or not. For instance, we can define the homogeneous Poisson process to model events that we can consider independent and identically distributed, in which the conditional intensity rate is just a constant value. We can think about dropping the identical distribution hypothesis using non-homogeneous Poisson processes, in which the conditional intensity rate is just a deterministic function over the space of our interest. But we can also consider the include dependence. The simplest way to include dependence is using the Cox process, in which the conditional intensity rate is a process itself that evolves on the same space of the point process. Now, actually, with these three cases, we are anyway lacking one possibility. What else can we have? Actually, it happens a lot in real-world applications that the point process depends on itself. What does it mean? The one event happening modifies the probability of other events happening in its immediate vicinity. This happens for sure for earthquakes. When the occurrence of an earthquake increases the probability of other earthquakes in its vicinity in time or space. But we may think also that crimes behaves in the same way. One crime happening causes other crimes in its vicinity, or for instance, car accidents, because they generate a congestion into the road network that causes other accidents. So what we would like to define a point process that is able to deal with this kind of excitation. This point process is called the Hawkes process, was introduced by Hawkes in the 1971, and we have the conditional intensity rate, okay, that is composed of a background rate, which is just a constant, plus a stochastic integral of some function, usually a decaying function that plays the role of memory in the stochastic process, in the point process. That in a simpler way can be written just as a constant rate plus the sum of the effect of all the events happened in the past ti, okay, happened in the past ti at the point in time t. This is a very simple example of Hawkes process, in which at the top we can observe the counting process, and whenever we have the counting process increasing by 1, we have a jump in the parameter, in the intensity of the process, that slowly decays as long as we don't have another event happening. So this is the simplest case of Hawkes process. Now, Hawkes proved that the Hawkes process can be seen also as a clustering process. You can think of a clustering process as the branching process for point processes, in which we have a background that is composed of immigrants that are, let's say, caused only by the background part of the conditional intensity rate, and then we have offsprings, which are offsprings of background events, but also offsprings of other offsprings, and they start from each of the event and as a non-homogeneous Poisson process with conditional intensity rate equal to the gain function. So this is what a Hawkes process is, and this is its clustering representation. Somehow, theoretically, we can disentangle the background from the excitation part. This model, 15 years later, was used by Ogata to produce the so-called ETAS model, that is epidemic type aftershock sequence model, in which each earthquake is assumed to have some triggering ability. Before the ETAS model, it was thought that just some main shocks had triggering abilities and the other aftershocks didn't have any. With this model, Ogata may include also the possibility that also aftershocks have some triggering ability. And he used conditional intensity rate using this formula, in which we have some background, which is non-homogeneous over the space, plus some excitation function that decays over space, over time, and also the triggering ability of the single earthquake I depends on its magnitude, mi. The good thing about about earthquakes is that Ogata had more than 1 century of literature about earthquakes that helped him define very reliable parametric form of the excitation functions. And knowing this parametric form, actually we can make inference on this model simply by maximizing the log likelihood with respect to the parameters of the excitation function. However, there is a drawback, there is a problem, because in order to compute this log likelihood, we also need to know the background rate. And we never know the background rate in advance, even its form. The standard solution usually is to use a kernel smoothing approach, in which we say that the background rate in point xy is just an average over all the points we observe, weighted with some kernel. The farther the point, the less its weight. But we should take this average only on the background events, not on all the events, because we are estimating the background rate. The problem is that point process doesn't come out with labels. We don't know which event is background and which is not. What can we do? So the solution was to define these two probabilities that are the probability of event J to be triggered by event I and the probability of event J to be a background one. Once we define this probability, we may use a weighted version of the kernel smoother in which we take the average over all the points, but each point is weighted with this probability of being a background event. Problem again, in order to compute this probability, we need to know the background. We need to know the excitation functions. So we are in a loop in which, in order to know something, we need to know the other. What can we do? We can use an algorithm called stochastic declustering that is based on the spirit of the expectation maximization algorithm, in which we start with an initial guess on the background rate, whatever guess we want. Given this initial guess, we get maximum likelihood estimates of the parameters for the excitation functions. Then we compute the probability of being a background event for each of the events. We get the weighted kernel estimate, the new updated weighted kernel estimate of the background rate. We get again the maximum likelihood estimate of the excitation function, of the parameters of the excitation functions. And if the gain in likelihood from the step 1 and step 4 has been enough large, we go on and go back to step 2. Otherwise, we just stop. Under the assumption that as long as more iteration we do, we get always better fit on the data, and the better the fit, the less is the increment that we have at each step. Now, the point is that when we are applying this model to earthquakes, we really know what's the parametric shape, in a reliable way, what's the parametric shape of the excitation functions. What about crimes and car accidents? We don't have any idea about what may be the shape of these excitation functions. So we need to find a solution, an algorithm, starting from this one, that helps us to estimate, as we estimated the background rate, also the excitation functions. This is the spatio-temporal Hawkes process, the general one, proposed by Moller in 2011, in which we have a conditional intensity rate that is composed of a background rate and the excitation part. Here you see those bars, because actually, since we are estimating stuff in a completely non-parametric way, we have too much freedom. We want somehow to constrain our estimation. So what we do is we assume that this background has average 1. We assume that these excitation functions integrate to 1, and we give the ability, and we set up these two parameters to adjust the level of the background and of the excitation. In this way, we make this model identifiable. Otherwise, it's not identifiable. We don't know anything about the shape of the excitation functions. So the idea is that we can think, instead of thinking of each event as being background or triggered, we think of each event as composed partially from background and partially from the triggering of the other events just before him. Obviously, the first event in time is only background because it cannot be triggered by anything else. The second event in time is partially background and partially triggered. The third, partially background and partially triggered by the first and the second, and so on. So we can come up with a kernel smoothing for the excitation function that this time does not target the single events, but uses pair of events and their lags, and each lag is weighted according to the probability that event I triggered event J, also both in time and in space. So the decimation, the stochastic reconstruction algorithm works pretty in the same way. We start on some initial guess on the background and excitation functions. We get maximum likelihood estimate of the relaxation coefficients mu and A. We compute the probabilities of triggering and of background. We get the new weighted kernel estimates. We get again the maximum likelihood estimates of mu and A, and we compare the likelihoods. If we are happy with our likelihood, we stop. Otherwise, we go on. We go back to step 2 and go on with the fitting. So now we get to the application. We tried to fit this model, first of all, to the crime data from the city of Castellón in order to see if there effectively is some excitation, some triggering between crimes in Castellón. This is the point pattern of the data. I skipped this image for the sake of time, maybe. And we considered the model we have just introduced with just the triggering, but also a model without any triggering, so only background. And we considered also some periodic model, because we had the idea that actually maybe criminality follows some periodic behavior along the week or along one single day, according to the hour, the time of the day. This periodic model just specifies the time part of the background to have some periodicity over the weekly component, and some periodicity over the daily component. We estimated all those models and we compared them in terms of log likelihood. Actually, this is the negative log likelihood. So the lower the negative log likelihood, the better they fit the model to the data. We found out that the best model is the one both periodic and triggering. And especially, in particular, this model estimates A to be around 0.04. A can be interpreted somehow as the total percentage of crimes in the city that is actually the effect of some triggering from other crimes. So there is not so much triggering, it's only the 4%, but I mean, it's not a neglectable part of the total crimes in the city. These are the background temporal estimation of the estimation of the background temporal components. We can see how during the blue line is the one estimated by the model. The red one is the one estimated on the raw data. We can see that the model is kind of coherent with the raw data. It makes sense since, as we saw, the triggering is not that much. And we see how in Castellón during the 2012 there's been a decreasing trend in the intensity of crimes, and it has, while it was stable during the last year. And according to the periodic component, we see how the most of the crimes are committed during the weekend days, and especially around lunchtime and dinner time. We can interpret this like criminal robbers wait for people going to have lunch or dinner at restaurants, and then they get into our house and rob us of whatever they want. I mean, this is just an interpretation. This is the background rate over space. We can see how the areas at greater risks are the one in the center, in the north, and in the south. And finally, we have the estimation of the excitation functions. What does it mean? These functions tell us how the triggering effect expands over space and over time when a crime happened here in space or here at point 0 in time. We can see how usually this excitation expands for like 1 kilometer around the occurrence of the crime, and usually decays to 0 in less than 1 day. This means that whenever there is a crime, if there is some triggering, this triggering will happen within 1 day and in a 1 kilometer range. We applied this model also to see if there is some triggering effect also in the car accidents data. These are car accidents happened in Rome between May 2017 and September 2017. We estimated the periodic and non-triggering model and the periodic and triggering model. In this case, the improvement in log likelihood given by the triggering is way more evident, and in particular, the triggering effect is estimated to be almost 0.13. This means that almost the 13% of the car accidents happened in Rome in this time window was an effect of the triggering by other accidents happened in its vicinity. These are, in this case, the curves estimated on the raw data and the ones estimated by the model are different, probably because the raw data don't take into account the triggering effect. We can see how we have a decreasing trend, a constant decreasing trend for the data, while the triggering model catches this minimum in August, and it makes sense. In August, Rome has no people around. People are out for holidays. No one takes the car. So it's normal to have this minimum peak in August. The same works for the weekly periodicity and the time periodicity. We can see how the the intensity of accidents, of car accidents, is high during the weekdays, while very low during the weekend, because people during the weekend go out for a trip or just don't take their car, stay at home. And while during the night there are not so many accidents, while there are more during the day. In particular, around lunchtime and dinner time, when people commute from work and their homes. This is the background of a space. Where the higher intensity is in the center of the city, and we can someone who knows Rome would recognize one of the main arterial roads of Rome, which are the Tiburtina, the Salaria, the Cristoforo Colombo, and the Appia, which are roads of very high intensity of traffic that is for sure related to car accidents, to the intensity of car accidents. And finally, we have the estimation of the spatial excitation and the temporal excitation. About the spatial excitation, we have a decaying of like 500 meters. Around the temporal excitation, this result is kind of weird. We have a temporal excitation that seems to not decay to zero even after 1 week. But the very weird thing is this periodic behavior that we observe here. Now we question a lot of ourselves about what is happening here. Why do we see this? It's not natural, and we found an answer to our question. This is a problem with data. Actually, we noticed that the policeman, when he records the accident, usually round the time of the accident to the o'clock hour or to the 30 minutes hour. For this reason, our model is detecting some periodicity in the lag between accidents that is not natural. So somehow we need to try to get less refined grid, or somehow redistribute accidents along the minutes in a uniform uniform fashion. So I get to the conclusion. We can conclude that the stochastic reconstruction provides us with a very flexible and reliable algorithm to estimate spatio-temporal Hawkes process for whatever context we prefer. And in particular, that car accidents exhibit a substantial triggering ability. I mean, the 13% is not a low amount. And about the further developments, it will be interesting to derive some penalized log likelihood, because naively comparing the log likelihood doesn't take into account the complexity of the model, the variability that is related to the variability of the estimation of the parameters, and so on. We should try to include also observation outside the area of interest. One big problem with this model is that whenever we have an event at the bound of the region, we need to assume that that event is background, while maybe it was just triggered by some event outside of our region of interest. And another problem, and another interesting extension will be to develop Hawkes processes that develop along networks instead of the R2 surface. And this will be very useful for the car accidents framework, in which accidents are not actually happening on the whole surface of Rome, but only upon the road network. So this is all. I hope this is not a goodbye, but it's a see you later, and maybe see you in 50 years.
thank you very much for the picture. The first one, so it was very nice. Yeah. I'm not going to say which guy I am. Questions? Victor?
How easy is it to extend your framework to a Bayesian framework? Maybe how easy is to extend this fragment or like estimation to something which is more Bayesian? In that way, maybe you can control for the problem with the data that is,
Yeah, sure. Yes, we actually this is one of the idea to somehow find a Bayesian way to estimate all these functions and non-parametric. We can use non-parametric Bayesian tools, but when the functions are continuous, it's not that easy. It may be very computationally expensive to estimate all those functions all together that interact with each other. But yes, it's an idea.
So you have that variable A, capital A, which tells you a little bit about the excitation.
Yeah.
Have you got some error bars around that, particularly for what was the middle one? The middle one was crimes, wasn't it? You had it at quite a small number, 0.04.
Yeah.
Is that significantly different from 0? Meaning, have you got some error bars?
When I talk about the problem with the estimation of this model is that when you use algorithm like the expectation maximization algorithm, they are just like very rude algorithm in which you cannot really estimate confidence intervals or error on your estimation. This is one of the big problems with this procedure from my point of view.
But you can estimate that numbers by the logical
Okay. Okay.
Ole?
Yes, so first a comment. Of course, the higher likelihood of car accidents around lunchtime and dinner time is criminals racing away in their getaway cars from the crimes. But my serious question was what's the stability of this algorithm? Can that blow up? Can it go wrong because it's this iterative thing? Is it always stable? Is it always?
Actually, it never happened, and we actually, even if this algorithm works for the same reason the expectation maximization algorithm works, there is exactly the same proof, because actually this step, when we make this computation, we are just taking the expectation with respect to the function we already have. This part here. And this part here is the maximization. So the stability of the algorithm is guaranteed from the same reason of the expectation maximization. And we try to run the models for our data from different starting points in different ways, and we always get the same result. Maybe the problem of the result is related to if you change the bandwidth of the kernel estimator, the results may change a bit, so you need to tune somehow the bandwidth of your kernel estimation, but this is the only stability problem, the tuning of the kernel bandwidth.
More questions?
So for some objects, it's also known that an action or an activation, for example, lowers the probability to be active in the next period. For example, for synapses, they have a refractory time where you cannot fire again.
Yeah.
Is it also possible to just change the sign of this excitation parameter to model?
Now, this is a very interesting question. This is something we're thinking about, because actually in this context it's kind of hard, because we need to guarantee that this term here is always positive. Okay, so this A negative puts the model in a very harsh situation, because it can be negative, but the sum here cannot ever be greater than the one here, and it's a bit of a problem. What we can think of doing is just defining this conditional intensity rate as the logarithm of this object here. In this way, we ensure positivity of the conditional intensity rate, and we can still keep the same relationship going on. So this may be an idea, but there is no literature about this. This may be a very interesting idea to do. Actually, this is what is usually done for the Cox process.
But the Cox process is also used for modeling epileptic seizures.
Yeah. Yeah. This is one of the applications. Is this one for epilepsy, seizures, Also, this problem was raised by my professor that works in capture recapture. Capture recapture is used to estimate the size of a population, in which you capture an animal and then you try to capture it another time. But the problem is that animals have trap happiness or trap happiness or trap shyness. So if you capture them the first time, maybe they're happy about the capture, they tend to be recaptured again, or they are not happy about the capture, they tend to not be captured again. So it would be very interesting to use this model to model the trap happiness, and maybe also find something find some solution to model also the trap shyness.
The trapping happiness, right?
Yeah, maybe you give him a treat, for instance, and then they tend to be recaptured again.
More questions? So if not, well, thank you very much.
You're welcome.
The last one today is